We're standing in this is the free electron laser, the UC Santa Barbara free electron laser, and this is the world's brightest source of radiation at terahertz frequencies. It's tunable from 100 gigahertz to 5 terahertz. 100 gigahertz is 100 times faster than the frequency of your cell phone uses to broadcast, and these frequencies are also way below visible light and heat. So we need this large apparatus, this free electron laser, to generate the tunable terahertz radiation. And the way it works is that the accelerator in the yellow tank is sort of a Van de Graaff type accelerator. It's like the one that you see when you're in high school. You put your hands on it and it makes your hair stand up. That one generates about 10 kilovolts. This one generates 6 megavolts, 6 million volts. So you can think of it as like a 6 million volt battery. We can tune the voltage on the battery between 2 and 6 megavolts. So that's that big yellow thing in the back. At the top of that, there's a cathode ray. There's a cathode, which is like in an old-fashioned television set. So it's a hot piece of metal, the electrons boil off of it, and then there's a grid that when you pulse it positive, it sucks the electrons off of that cathode. Now those electrons are seeing this 6 million volts of potential difference from the big yellow battery back there, so they get accelerated up to nearly the speed of light, and they go into this beamline. They go around the beamline, bent by the blue dipole magnets and focused by the red quadrupole magnets, and make their way into the undulator. The undulator is the business end of the free electron laser. That's where the intense terahertz radiation gets made, and that intense terahertz radiation is what is ripping the electrons away from the excitons and causing them to recollide, ripping the electrons away from the holes and causing them to recollide. So we need a very powerful source of electromagnetic radiation. That electromagnetic radiation is coming from the undulator. And so the electron beams, as they go through that undulator, they're going through alternating north and south magnetic fields, and the electrons are wiggling, and the frequency that they broadcast at is this terahertz frequency, which is going to be ripping apart the excitons, and it's determined by how fast the electrons are going and how far apart the magnets are. Once the electrons go through that undulator, they actually get collected back into the big battery, into the accelerator. And the light that they generate, the terahertz radiation that they generate, gets piped out into the labs in the next room where the experiment actually takes place.
So as Mark Sherwin had told you, that here at UCSB we have free electron lasers, the brightest source of terahertz radiation essentially in the world. And so we're using this bright terahertz source to create recollisions between electrons and holes in semiconductors. And to do that, we need to create the electron-hole pairs, the excitons, using a near-infrared laser. That's over here on the left. And then we use the terahertz light to really rip the electrons out of the excitons and then force them to kind of recollide with the hole that they originally left behind. And when they do this, the extra energy that they've gained in this process gets emitted as kind of new photons at a different frequency. And that's all collected and analyzed by a spectrometer and a photomultiplier tube. In the course of this experiment, we have near-infrared light from a near-infrared laser here, and this near-infrared laser travels down this path, focuses around, comes through, and hits our sample here, and then kind of continues out this way towards this monochromator. At the same time, terahertz light is coming down the path here, comes up off this mirror, off this one, and focuses down here to our actual sample. The sample itself just sits in the cold, and it is the medium that is used to mix this intense terahertz light and the near infrared light together.